Hello, welcome to Grade 12 Calculus 90 Minutes. This video is intended as a quick guide to show you the ropes of calculus, or as a refresher. This video will detail the basics of calculus at grade 12 level. For the sake of time, I had to cut some content, but this video contains what I feel are the most important topics. Let's start off by asking, what is calculus? Calculus is the study of numbers and how they change, typically when the change is extremely small. There are two primary branches of calculus, derivatives and integrals. Grade 12 focuses on derivatives. Derivatives involve finding the change between two values, also known as the slope or the tangent. You can see on the diagram in the bottom right, the tangent of a point has been found. Calculus was independently discovered by Isaac Newton and Gottfried Wilhelm Leibniz at the same time. You'll see some of the ramifications of this in the future. Limits are one of those important concepts in calculus. It tells us what happens as a parameter of a function approaches a value. You can see in this example, L is equal to the function f of x as x approaches b. Here, we will solve the limit of x squared plus 3 as x approaches 3. First, we'll define our limit like was shown in the previous slide. We'll also substitute our variable for the value it's approaching. So in this situation, we substitute x for 3 as it is approaching 3. Then, we can solve to find our limit. And our limit is equal to 12. Let's change focus for a minute and talk about finding the tangent of a line. In the past, we've used this formula to find it. This requires 4 separate variables to solve and is very time consuming. It also can't give us an accurate tangent at a point. We can generalize this equation to this form, where f of x is equal to the y value and h is the difference between x1 and x2. We can reduce it even further to just be f of x plus h minus f of x divided by h. The diagram in the bottom left shows how h factors into the tangent. Let's now combine limits in this new form of finding tangents. Let me ask you, what would happen as this h value approaches 0? Well, as it approaches 0, we can get an accurate value for the tangent of a point. This is what a derivative is, and we can use a limit to find it. Now, let us find the derivative of x squared. First, we'll need to find the limit of the tangent, so we'll arrange it like this. We'll then use the formula to continue solving the equation. So we'll square both those terms. And then we can combine our like terms now. This leaves us with 2xh plus h squared divided by h, which we can divide out, which leaves us with 2x plus h. And with the limit meaning h is equal to 0, our answer is therefore 2x. So that means the derivative of x squared is 2x. So, our answer is 2x. What does this mean? 2x is the derivative of x squared. Any value solved for in the derivative is equal to the slope at the same point of the function we took the derivative of. Clearly, this is much faster and more accurate than the method we used before, and it's very useful in calculating change. So, you might be asking, how do we show derivatives? Remember Newton versus Leibniz? This is one of the major differences, notation. In the Leibniz notation, we use d over dx next to the function we took the derivative of. You can see that on the top. For Newton, we add an apostrophe beside the function we took the derivative of. You can see that on the bottom. Lucky for us, we don't have to do this big equation every time we want to take the derivative of a function. Instead, we can use different rules to make this easier. For example, the power rule exists, which allows us to solve functions that have a power directly to x. To use the power rule, you take the exponent and multiply x by it, then subtract 1 from that value, and make it the new exponent. You can see an example on the bottom there. Another example of a rule is the chain rule, which is used when terms or functions are being used inside one another. We take the derivative of the outer function and leave the inner function, then multiply the whole thing by the derivative of the inner function. Here's an example. We'll start with the function x squared plus 3 squared. We'll then take the derivative of the outer function, which gives us 2, leave the inner function, then multiply it by 2x, the derivative of the inner function. Then we can combine our terms, which gives us 4x times x plus 3. The product rule is used when finding the derivative when two terms or functions are multiplied. You take the derivative of the first term, multiply by the second, then add the derivative of the second term, multiplied by the first. For an example, we'll start with 3x squared times 5x squared plus x. We'll find the derivative of 3x squared, which is 6x, and multiply it by 5x squared plus x. Then, we'll add 3x squared times the derivative of 5x squared plus x, which is 10x plus 1. We can then multiply it out, which gives us 30x to the third, 6x squared, 30x to the third, plus 3x squared. We can then combine our terms, which gives us the simplified answer of 60 times x to the third, plus 9 times x to the 2. Quotient rule is used to solve derivatives when two terms or functions are divided. You can do this by taking the derivative of the numerator multiplied by the denominator, and then subtracting that by the derivative of the denominator times the numerator, which is all then divided by the denominator squared. For this example, we'll start with 3x squared plus 4 over 5x to the fifth. We'll then apply the quotient rule to give us 6x times 5 to the fifth minus 3x squared plus 4 times 20x to the 4 divided by 5x to the fifth squared. We can then use the distributive property to give us 30x to the sixth minus 60x to the sixth plus 80x to the fourth all over 25x to the 10th. We can then combine our like terms to give us negative 30x to the sixth minus 80x to the fourth all over 25x to the 10th. When finding derivatives of trigonometric functions, we need to memorize what each is derived to. We can see here, sine becomes cos, cos becomes negative sine, and tan becomes secant squared. The second derivative occurs when the derivative is taken of a derivative. In Newton notation, it is represented by adding an additional apostrophe. You can think of the second derivative as being the acceleration, or the rate in which a slope is changing. Here's an example of taking the second derivative. We start off with the function f of x equals x to the third plus 2. Then we use the power rule to make that 3x to the 2. And we use the power rule again to make it the second derivative, which is 6x. Derivatives can help us understand graphs and how functions behave. When the first derivative is positive, the line is traveling upwards. If it is negative, the line is traveling downwards. And if it's equal to 0, a vertex exists where the line isn't moving. The second derivative is useful in finding the concavity of a line. That is, if the first derivative is getting bigger or smaller. If the second derivative is negative, the slope is decreasing, and if it's positive, the slope is increasing. Thanks for watching Calculus in 8 Minutes. If you have any comments, questions, or ways I can improve my video, please let me know in the comments.